really parameter, because the vector has x component, y component, and the z component, and those are those components are a function of some variable t. So that is vector equation. So we'll work with parameterization, and then actually in this parameterization, can we express motion, everything, and we will see it. And then we are going to talk about vector field, and that vector field is telling us the flow of forces, velocity, gradient, you name it, and we'll see all this fashion. All this preparation was actually for dealing with vector analysis. All right, so yesterday and before yesterday, I gave you the parametric curves, and I will give you summaries, but I will show you, as I said, on Tuesday, to show you 2 more examples, and we'll go to motions, and thereby actually we can see how position vectors will give us the velocity vector, acceleration vector, and so on. That is really dealing with dynamics. And let us go straight to the problem. Okay. So let me switch camera. And now what I want to start working on this problem. Find the point at which the line x is equal to t, y is equal to 2t, and z is equal to 1 plus t pierces the sphere of radius 10 centered at the origin. All right, start working with this problem. Yeah, as I said, everything is can be expressed in terms of vector. For example, this one, if you really write it, r of t, which is equal to x, y, and z component it has. And that is going to be actually t, 2t, and 1 plus t. And if you want, actually, you can really change this one into the form. Equation of a line is r of t is equal to, last time as I showed you, r sub 0 plus t times v. And from here, you can really write it. The coefficient here, 0, 0, and 1 you have, plus t times 1, 2, 1. And this is really the vector equation. And now the equation of the sphere of actually of radius 10 will be what? X squared plus y squared plus z squared is equal to 100. Now, to find the intersection, what do we do? Well, when this is the sphere and it is pierced by the line L, so at least 2 places it is going to pierce it. Can we find that? Well, piercing means what? They have a common point. This line L and this sphere, let's say pi, has a common intersection point. Commonality means what? Well, we have to enter the parametric equations of the line into this. That is a common point. That means what? X squared is t squared plus y squared is 4t squared because 2t when you square it, and then 1 plus z squared 1 plus t squared when you square it, and it is going to be t squared plus 2t plus 1. This equals 100. Is it clear what I'm talking about, guys? All right. Then now let us really solve for t. If we get the parameter t, then actually we can find the corresponding value of the point x, y, z, because x is a function of t, y is a function of t, and as well z. So we have how many t squared? 6t squared plus 2t minus 99 is equal to 0, because we have 100. When I bring everything, because it's quadratic, it becomes this. Then now, because it is quadratic, t has possibility of two solutions, t1 and t2. And by using the quadratic formula, minus b, that means negative 2, plus or minus square root of b squared, which is 4, 2 square is 4, minus 4 times a, which is 6, and c is negative 99 over 2a, 2 times 6. And this will give us negative 2 plus or minus square root of, okay, when you multiply this 24 times 99, it is going to be 2376, 72 plus 476. So 2376. You can check with your calculator, guys, over 12. And from here, I can get two possible solutions.
I got a 2380 in the radical there.
2380?
Yeah, I think you might have forgot to add the 4.
Okay, right. So, yeah, I have to add 4, yes? Okay,
Yeah.
Thank you. Now take the square root of this one and add these two with negative. Add them and you will take negative values. So what do you get?
So
4 point.
you mean like decimal approximations? I usually just leave the radical.
Because we have to plug it in.
Right. The positive one, I get the 3.89877.
So shall I make it 3.9? Is that
Sure.
okay? Okay. And the second one, please.
Let's see. That is this guy.
Negative 4.23, maybe?
Yeah, just a moment. I haven't found that one yet.
Okay.
Did you say negative 4.23?
Yes.
Yeah.
Okay. So we have these two values. So in other words, here what you have to do is t is a parameter, and the domain of t is already number. We don't drop it here. You have to really remember. Then now when t is equal to 3.9, the first one, t1, then the x value, x is equal to 3.9, y is equal to 2 times 3.9, which is equal to 7.8, and z equals 3.9 plus 1, which is equal to 4.9. So the first points are x, y, z. That is 3.9, 7.8, and 4.9. And now, when t is equal to negative 4.23. X is equal to negative 4.23. Y is equal to twice of negative 4.23. That is equal to actually negative 8.46. And Z equals negative 4.23 plus 1, which is negative 3.23. So in this case, X, Y, and Z are going to be what? Well, this point, negative 8.46 and negative 3.23. Well, it makes sense. On the one side, you will get actually all the negative value. On the other end, when the line is really piercing, it goes corresponding positive values. Or sometimes if it is going like this one, you can see also the other one. So it makes little sense. Is it clear, guys? So this is really parametric representation, the intersection between the surface and the line. That's what we are going to do. Well, now, how about if it is a moving object? When it is really moving parametrically, the parameter is really telling us what? Not only where it is located, a point in the X, Y, Z plane space, but also at what time it is going to reach. So if I have actually one path like this one, and the other is really going this way, and I have two paths. Well, now these two paths, they have so many alternatives. One, they can intersect, and they intersect at the same time. The other one, they can intersect, but at a different time. If a particle is moving this way, this object is reaching this point at a certain time, whereas the other object, which is here, reaching the same point at a different time. Third one, probably one is passing over the other. That means they never intersect. Seemingly, this path is going to be on top of, with a certain space, this curve. For example, the highway overpass. If you see the curve from the space, what will happen is you will see the curve at the same point on its projection twice. That means it was underneath the path, and then it will pass through that, and this come here. So although this seems same point when you look at it, but in a coordinate system they are not, because they have different z coordinates. All right. So based on this, let's do one example. Two particles move through space with equations. The first one, R1 equals Ti plus 1 plus 2Tj and plus 3 minus 2Tk. And the second one is negative 2 minus 2Ti plus 1 minus 2Tj and plus 1 plus Tk. Do the particle ever collide? Do their paths cross? If they collide, of course, then. But if they are not colliding, that means they might cross also, or they might not. So find out, try, and then we'll work it together. So what I suggest here is to see if the particles collide, we must find out if they pass through the same point, single point, at the same time t. That means what, guys? The path by R1 must be equal to the path with R2 and with the time. And that means what? If two vectors are equal, x has to be equal with the other x, y has to be equal with the other y, and z equals with the other z. That means x1 and x2, y1 and y2, z1 and z2. X2, Y2, Z2 are the component of R2, and X1, Y1, Z1 are going to be the component of actually Z1. Well, now that means this will lead me what? The X component for this one is T, and it has to be equal to with negative 2 minus 2T. And for this one, the Y component is 1 plus 2T equals 1 minus 2t. Remember, that is what we learned. If two vectors are said to be equal, what do we say? They have to have the same components, because equality of vector determined not only by magnitude but also by direction. So these components are actually embodying both magnitude and direction if they are equal to one another. All right, and that is the principle we are using. So moving forward, 3 minus 2t has to be equal to 1 plus t. And now what we have to do is we solve for from 1, because we have 3 equations and one unknown, that is t, and we can solve from either of the equation for t. So using this one, if I try to solve for t, I have 3t equals negative 2, and from here t equals negative 2/3. Well, now if I want, I can plug this one into these two equations, and I will get a false statement. Or I can do also solving here. If I get the same t, that is true. If I get different t value, then I have a problem. So when I bring this to the other side, it is 2t plus 2t, which is 4t, equals, and 1 by 1 will be cancelled, it is 0. That means t is equal to 0. T is equal to negative 2/3 is different from t is equal to 0. That is enough. But to see the third one is also, if you look at here, you have 3t, because bring negative 2t on the other side. So 3t equals, from 3 you subtract 1, it is 2. Therefore here t equals 2/3. So all the 3t values are really different. Surprise. Even if it doesn't satisfy one of the two, then there is no really a common point at the common time. So what is this telling us, guys? Do they collide or not? There is no common solution, and the particles do not collide. All right. Well, now your turn. I will give you about 3 or 4 minutes. If they are not colliding, at least do they have a common point? In other words, do they get at that point at a different time? So work through that. Do you agree? Do you guys agree with me? To see if their paths cross, what we need to do is find out if they pass through the same point at two different times. Let us call these two different times T1 and T2. It has nothing to do with calculus. This is really algebra, and justify it, please. Okay, let us work through this one quickly and move on to the next one, actually, the next section. All right, so you just copy these equations. In other words, T1 has to be equal to negative 2 minus 2T2 and 1 plus 2T1 must be the same as 1 minus 2T2 and 3 minus 2T1 has to be equal to 1 plus T2. Okay, T1 for the first particle, T2 for the second particle. These are. And then now what we are going to do is you have actually three equations and solve for one of the variables and plug it in the other two. And if it's satisfied, then actually that is really okay. So by plugging, T1 is already solved here. So let us plug it into these equations. Okay, and that means 1 plus 2 times negative 2 minus 2T2 equals 1 minus 2T2. And this will give me actually 1 minus 4 minus 4T2 equals 1 minus 2T2. Okay, one by one will be cancelled. So we'll bring both actually t values on one side. So this will really telling me 2T2, because here negative 4, when you bring it, is really 2T2 equals negative 4. So T2 equals negative 2. Well, let us see here also. If I get negative 2, then it is satisfying, then that is all right. And we'll check it. All right. Then now what is really happening is 3 minus 4 minus 4T2 equals 1 plus T2. And then now this is 3. By the way, negative and negative will make it positive. I'm sorry. And here also it is positive. Nobody really corrected me. All right. Equals this. So now when you really solve this one, what do we get? Well, 1 will be cancelled, 6 equals, and when you bring this 40 to the other, it is going to be negative 3 T2, and that is actually T2 equals negative 2, and that is true. Okay, well, Are we done, guys? So if they are really passing, what is the point they are going to pass? Well, you can use actually the point, for example, for T1, by the way. Then what is really T1? T1 is going to be negative 2 times, minus 2 times T2, which is negative 2. And that is going to be actually negative 2 plus 4, which is equal to 2. So when I plug 2 here, T1, the X value is 2. And when I plug actually 2 here, it is 5. And when I plug 2 here, actually negative 1. That is the point. Well, I'm better get also here the same result. Now in this case, I'm going to put negative 2. Negative 2 minus 2 times negative 2 is 2. And when I put actually 1 minus 2 times negative 2, that is really 4 plus 1 is 5. Then when I put negative 2, 1 minus 2 is negative 1. And as you see, these 2 points are equal. And yes, they have a common point. 2, 5, 1. While the first object reaches that point at t is equal to 2, the second particle is reaching that same point at t is equal to negative 2. That is what it means. Okay, well, the main really knowledge is not only solving, but we are going to require to parameterize actually curves, any vector valued function. So why not I summarize what we have done yesterday, before yesterday, and even today, in order to parameterize the curve. The common curves that we are going to encounter are actually functions determine any, it can be quadratic, polynomial, and so on. The other one is curves such as ellipse or circle. And the other one is a straight line. That means a line segment, for example. And let us really see how we can really parameterize all of those. And well, we have done it, but I'm going to really see. Okay, when a curve is an ellipse of the form x squared over a squared plus y squared over b squared is equal to 1. When you are parameterizing counterclockwise direction, that means the x value has to be cosine and the y value has to be sine. So a cosine of t, y equals b sine of t. And if you want to make it clockwise, you have two possibilities, either making one of them negative. So x is equal to a cosine of t, y is equal to negative b sine of t. This will really help you. And depending upon also the starting point, whether it is on the x coordinate or the y coordinate, the starting point, you can reconvert these sine and cosine actually orientation. And of course, one complete revolution will take place when t is between 0 and 2 pi. If it is a circle, there is no difference. It is the same principle, except a and b are going to be the same. It is r. So x squared plus y squared is equal to r squared, circle. So what you are going to be is, again, for counterclockwise, x is equal to r cosine of t, y is equal to r sine of t. And if it is clockwise, x is equal to r cosine of t, and y is equal to negative r sine of t. Here, negative, you can put. And that is what you have to do. And suppose y is a function of x. Then you can really come up with so many parameters, but the common one, just let x is equal to t and y is equal to f of t. And if actually x is a function of y, x is equal to g of y, let y equals t and x is equal to g of t. You can really make those. And line segment, of course, we derived it, but I didn't prove it. The line segment r of t given by 1 minus t x sub 0, y sub 0, c sub 0. What you are going to do is from this point, x sub 0 to x sub 1, and that is really what you are going to do. 1 minus t, this is a scale factor multiplying the initial vector plus t times x sub 1, y sub 1, z sub 1. And remember, t is changing from 0, starting point, and the end of the line segment destination is 1. Or you can write it in a parametric. This is a vector form. But if you want to write it in a parametric form, component by component. 1 minus t x sub 0 plus t x sub 1, y equals 1 minus t y sub 0 plus t y sub 1, and z likewise. And in this case, if this vector, instead of really a space vector, if it is a plane vector, what we are going to do is really drop the z component, and that's it. I hope this will really summarize and will give you a good hint for you actually in the future when you parameterization. Okay, is it clear, guys? Shall we move forward? All right. Now then, let us talk about motion, velocity, and acceleration. That is actually 7.2. I will start this one. I probably am going to give you lots of examples, and those examples are probably you have seen them before. Maybe you didn't really have done it in vector form. So we are going to place those, and then actually everything from now onwards is going to be expressed in terms of vectors. So in this section, we see how to find a vector quantities of velocity and acceleration from a parametric equation for the motion of an object. Well, the first one, the velocity vector of a moving object is a vector v. The magnitude of vector v is the speed of the object, and the direction of vector v is the direction of the motion. Thus, the speed is what? The norm of, or the magnitude of v, and it is always tangent to the object path, as you know it. So based on this, let us really do one example. And here it is, the example. A child is sitting on a Ferris wheel of a diameter 8 meters, making one revolution every 2 minutes. Find the speed of the child and draw the velocity vectors at 2 different times. All right, so you can pick time and so on. So a child is sitting on a Ferris wheel, that's it, and it has a diameter of 8 meters, making one revolution every 2 minutes. And I want to come up first with the position vector. Then if you have that position vector, differentiate it and find the velocity vector, please. And then you can really draw the position vector and the velocity vector at 2 different times. By the way, you have to remember about angular velocity. The angle is changing when it is rotation. So instead of t, what you are going to be, it has to be omega t. X is equal to r, depending upon what you are going to do, either cosine or sine omega t, and likewise also. All right, we are running out of time. Shall we do it together, guys? All right. So let me really give you what is really given. The radius. Is the radius given? Because the diameter is 8, therefore the radius is going to be 4. Okay. And now what we are going to do is the object is really, the child is moving at a constant speed around. So the distance it is really moving is 1 complete revolution, this d. Let me call it distance. And that is what? 2 pi times the radius r, which is or the diameter, which is 8 pi. You guys agree? So the distance is this one, and the speed. The speed is actually the magnitude of the velocity, and that is actually what? Distance divided by time. So the distance is 8 pi and divided by time 2, which is 4 pi. It's approximately what? 12.57 meters per minute. That is it. So the direction of motion is tangent always to the circle. We proved it already before. And then what we need to do is, so if this is the center, the radius function, the r is this one, and r prime is going to be pointing, which is v. Or if I want really here, always, if you have a circle, the tangential actually of the vector is always perpendicular, and that is really v. And that's it. What is this one is really giving you in general, but I didn't write it in component form. But for the component form, r of t, whether it is space or what you are going to do is f of t I plus g of t j plus h of t k you have. In our case here, it is really a plane curve, so you can cross out this one. Then what will be the velocity? dr dt. That means df dt I plus dg dt j plus dh dt k. So if you want actually for that, that is what we are going to do. And the speed is going to be what? And we usually represent it without vector because it is scalar. It is the magnitude of actually v of t. And that is going to be square root of dr dt squared plus df dt squared dg dt squared plus dh dt squared. That is what we are going to really work on. And this is it. And by the way, you can really represent this in terms of vector equation r of t equals a cosine of omega t I plus b times sine of omega t j. You can write it. And then your a is actually the radius, which is 4 cosine of omega t I plus, because it is a circle, 4 times sine of omega t and j. By the way, this one I gave you for ellipse. Generally, when a and b are equal, it is r, and that's what we are going to do. Now, what do you do? To find omega, what we are going to do is one complete revolution is 2 pi divided by omega equals what? It is really making every 2 minutes. That means 2 pi equals 2 omega. That means omega is equal to pi. So you have 4 cosine of pi t I plus 4 sine of pi t j. That is how you are going to write a vector equation. Then take the derivative, and then actually the length also you'll find it, by the way, by making this formula. The speed and the length also you can really find by the finding the magnitude of this vector component, and you'll get the same answer like this one. But we do this elaborated problem when it is really giving given a vector equations from the general. So we'll do this kind of problem tomorrow, and we will see different properties that we have seen before, but we didn't prove them. For example, always the acceleration vector with a constant speed is really pointing towards the center. Is that true? Or the velocity vector, if it is a circular path, is always tangent to the path, and so on. We will prove all that. Thank you for your attention, and I will see you tomorrow. Please be ready for the quiz also. Okay, I send you, even those of you who didn't read the announcement, I emailed you also using your regular email. Probably you guys will not have a problem because you are regularly coming here, but there are some students who are not really attending, so I don't want them to miss out. So I don't worry about you anyways. All right, thank you. See you tomorrow.
Thank you.
All right, take care, guys.